Good morning. Today we will do lesson 29 on diagonalizability. So let me recap with a few ideas from before. So first, I'd like to remind you about the question of what does it mean to be diagonal? So let's say that T is a linear transformation. So remember that we say that T is diagonalizable remember this means able to be diagonalized if we can find a basis for our vector space V such that this matrix representation with respect to the basis beta is now a diagonal matrix. Now, one way in which we can determine that a matrix is diagonal is we have to look at the related concept of eigenvalues and eigenvectors. So we say that a non-zero vector, let's call this lowercase v inside of our vector space V, is an eigenvector for our linear transformation if there is a scalar, let's call this lambda, such that T on this vector V is lambda times V. Right? We call lambda the eigenvalue associated to V. Now this, of course, is for a linear transformation, so we can do this similarly for a matrix. So given an n by n matrix, then of course we can say that it is diagonalizable really if we can find a matrix Q that is an invertible matrix Q such that this matrix, let's call it B, this Q inverse AQ is a diagonal matrix. And then finally, we could talk about the concept of an eigenvector. So finally, a non-zero vector V inside of this Fn is an eigenvector if, of course, A times V is lambda times V. Okay. So So again, we have this concept of what does it mean for a linear transformation to be diagonalizable? What does it mean for a matrix to be diagonalizable? What does it mean to have an eigenvector or an eigenvalue for a linear transformation? And then similarly, an eigenvector and an eigenvalue for a matrix. So with these definitions, we had a major result, and these were 4 theorems together. So these are theorems 5.1 through 5.4. And here now we want to write down 3 objects. Let's say that T is a linear transformation. Beta is a basis for V. And let's let A be this matrix representation. So with these 3, there are 3 results I'd like to write down. So first, T is diagonalizable if and only if our basis beta consists of eigenvectors for T. And moreover, this matrix representation A is a diagonal matrix whose diagonal entries let's write these here as lambda j, are the eigenvalues for T. So again, the basis says something about the eigenvectors, and the diagonal entries for the matrix representation says something about the eigenvalues. So that's the first of 3 results. So here's the second one. Given a scalar, the following are equivalent. So there are 4 statements I'd like to make here. First, lambda is an eigenvalue. But an eigenvalue for the transformation T. Second, lambda is an eigenvalue. But now for this matrix A. Third, if I consider the determinant of this n by n matrix, right, this A minus lambda in, that determinant is 0. And fourth, there exists a non-zero vector, right, so V does not equal to the 0 element. I want V to be an element of this null space. So here, this is our transformation T and I'm subtracting away the scalar times the identity transformation, so the one that sends x to x, and I want the null space of that. So everything here such that when I take this linear transformation on x, I get back 0. So this space here, we're going to study in detail today. So I'm going to define this here as E sub lambda. So again, we're going to focus on this in a lot of detail today. So these 4 statements here are equivalent. And finally, let's consider this polynomial. This f of t, which is the determinant of this n by n matrix. So there's 2 things I want to say here. First, this is independent of the choice of basis. Remember that the A here, this matrix, does depend upon the choice of basis beta. But after I take the determinant here, it really doesn't matter what beta is. Moreover, lambda is an eigenvalue. If and only if f of lambda is equal to 0. So what this last part here says is, once I stare at this polynomial, the roots of this polynomial correspond to the eigenvalues. So that's something else that we're going to play around with quite a bit today. Right. Now there was another result that we gave that really focused on kind of this whole question here of, what do we know about the eigenvalues? So this in the book is theorem 5.5. So with the same notation as before, let's assume that our transformation T has k distinct eigenvalues. And let's call these eigenvalues lambda 1 through lambda sub k. If we have a collection S and this is a collection of vectors, I should say here, collection of non-zero vectors, and they have to satisfy T of Vj is lambda j Vj. Right, so I take each of these here, apply T to this, and I get back a lambda times Vj. Then S is a linearly independent set. So there's a direct consequence of this. So this here says, what if I have k distinct eigenvalues, not necessarily n of them, but just k of them? Then here I have a linearly independent set. In the specific case, if k equals n, then T is diagonalizable. Now remember that this result here really built upon 2 examples we discussed last time. So maybe here, I'll just kind of recap these two examples. So for example, let's let our transformation T be the reflection about a line So remember last time we talked about this idea here of a reflection about a line. And we knew here that we have two eigenvalues. In fact, we have two distinct eigenvalues. Namely, lambda 1 was plus 1, and lambda 2 is minus 1, corresponding to the eigenvectors. And let's just put this here into a set, some set S, which consisted of these two vectors, which I'll write out this way. So that's 1 over square root of 1 plus m squared, 1m. So something similar over here, 1 over the square root of 1 plus m squared. And here I have a minus m1. Well, here I have two distinct eigenvalues. I'm going from R2 to R2, so everything's two-dimensional. Well, we already know that our transformation is diagonalizable, but actually in this case, we knew that S is the basis. Right, so again, here, k is equal to 2. I have two distinct eigenvalues. As another example, let's consider this IV going from R2 to R2, and this is the identity map. And remember that all that this does here is it just sends a vector x to itself, so it really doesn't do anything. Well, we actually only have one distinct eigenvalue. Namely, lambda 1 and lambda 2 equal to plus 1. However, we know that this map here is diagonalizable. So here's a weird concept. If I have n distinct eigenvalues, then T is diagonalizable. However, the converse is not necessarily true. If T is diagonalizable, I don't necessarily have n distinct eigenvalues. Like over here, I have a transformation that is diagonalizable, but it does not have two distinct eigenvalues. So what we're going to do today is really focus on the following motivating question. If a transformation does not have n distinct eigenvalues, call this transformation T. Try to be more precise. If this has k distinct eigenvalues, but k does not equal n, when is T diagonalizable? So that is, when do we have something like the second example here? So as promised, here's where we're going to get into properties of this set. So I want to discuss the concept of multiplicity. So what the notation is before, let's set things up in the following way. Let's say T is a linear transformation. Beta is a basis. We have the matrix representation A. And let's make one more here. And let's say that T has k distinct eigenvalues. Right, so just like the notation from above. So to be precise, we can consider the characteristic polynomial So this was this f of t that we defined from before. Now, because this is a polynomial of degree n, then it turns out that we can kind of write things in this way here. So I have a constant term, I have some linear term, I have some quadratic term, all the way up to this highest power, this leading term. So again, these here are just going to be some kind of constants that all depend upon our matrix A. Well, it turns out that this actually can factor in the following way. So here I've factored my polynomial, and the mk's here are just some exponents. So these are non-negative integers. We actually call these, this mj, the multiplicity of the eigenvalue, this lambda j. So again, I compute my characteristic polynomial, I factor the polynomial, and then I get various exponents here, and this exponent, this power, is what I'm calling the multiplicity. So we'll give an example of this in just a moment. Let me just finish my definitions here. Now let me just make a couple of quick remarks. First of all, if I sum the exponents, so here I have m1, m2, mk. Well, if I sum the exponents here, then it actually tells me how many times t appears. But t appears n times. So this here, of course, is the dimension of our vector space. Right? Also, I'll just put this out here. Given lambda and f, we want to focus on the following subspace. This E sub lambda, which is the null space of T minus lambda IV. And really, if you expand all of this out, this here is the set of vectors in V such that, well, of course, if I stare at this here, when I apply all of this to V, I should get back 0. And if you just stare at it long enough, then this E lambda is exactly this space here. All right, so again, E lambda here is the set of vectors such that T of V is lambda V. So again, I'm fixing lambda, and I'm asking about this space here. So eventually, we'll show that the dimension of this subspace is at most m sub j, when lambda here is lambda j. So these are subspaces, and I can compute the dimension of these subspaces, and they're going to be related to this multiplicity. Okay, so before we get there, of course, let's do some examples to figure out what's happening here. So let's do first example. Let's consider IV going maybe from F2 to F2. Then with respect to the standard basis, let's maybe call this gamma. So remember, this is just what we worked out in the last lecture. Then our matrix A will be this matrix here, which of course is just the identity matrix. And so we computed last time that the characteristic polynomial was simply t minus 1 squared. Right? So again, we worked this out in the last lecture. So in this case, we see that there is only one distinct eigenvalue. And of course, that eigenvalue is lambda 1 equals plus 1. And our multiplicity, m1, is equal to 2. right? Because there's the exponent there, t minus 1 squared. So the exponent is the multiplicity. The root here now is plus 1. Right. Now let's do a second example. Let's consider the transformation. Let's say LA defined by this matrix here. All right, so 1, 1, 0, 1. So now if we compute the determinant of A minus T I, then here I would have a 1 minus T, 1, 0, 1 minus T. Right, so if I just work this out here, and I'll simply say that again, you get a T minus 1 squared. So also, we get the K is 1. Right, just one distinct root. And that eigenvalue is plus 1. And again, the multiplicity of this eigenvalue is 2. Right, so these are two different matrices. One is the identity matrix, one is not. They both have the same characteristic polynomial. And I can read off the eigenvalues. In this case, there's only one distinct eigenvalue. And I can read off the multiplicities. In this case, the multiplicity is 2. Right, let's do a slightly more complicated example here. So let's consider LA. Now here, let's do this for F3. And let's say that this is defined by this 3 by 3 matrix, which is 3, 1, 0, 3, 4, 0, 0, 4. So let's try to ask, what is f of t? So we're trying to compute the determinant of this matrix, 3 minus t, 3 minus t, and then 4 minus t. Okay. Now, remember that the determinant, in this case, we have an upper triangular matrix. The determinant is the product of the diagonal entries. So observe that A minus TI3 is upper triangular. So again, the determinant is just the product of the entries. So now if I move things around just a little bit here, then I can write this as -1 times t minus 3 squared times t minus 4. Right? So here now we have two distinct roots. Which really means we have two distinct eigenvalues. So the first eigenvalue is 3, and the multiplicity is 2. The second eigenvalue is 4, and the multiplicity is 1. Right, the way that we get that is the first root here corresponds to this eigenvalue, and the exponent here is the multiplicity. For the other root here, I get this is the eigenvalue, and the exponent here is the multiplicity. Right. So again, you may want to compare that to this expression over here. So I have some choice of sign, some plus or minus 1 that I'll kind of ignore. Then I want to have these linear factors here raised to various powers. Right? And the powers here are what I'm calling the multiplicities. So now, what I want to do is ask, how is that related back to this over here? Right? This E lambda. So let's do a couple of different cases. So first, let's take a look at maybe lambda 1. So remember that this is the set of vectors. All right, so again, here I'm just plugging in lambda is equal to 1. So the set of vectors such that A v is lambda 1 v. And so here, we can just stare at this a little bit. So here I want those vectors. Let's write them in terms of x, y, and z. Now, if I were to take A times x, y, z, going back to this definition over here for A, then I get back a system of equations that looks like this. So 3x plus y equals something, 3y plus 4z equals something, then 4z equals something. So over here on the left is A times v, and over here on the right, I have to take lambda 1 times v, but lambda 1 is 3. So if I take 3 times v, this will be 3x, so be 3y, so be 3z. All right, so say that one more time. The left-hand side over here is A times this vector. Right, remember that A was this matrix back here. The right-hand side is lambda 1 times this vector, but lambda 1 we said was this eigenvalue 3. So if I stare at these here, then for example from the first equation, I can cancel 3x from both sides, and I get y equals 0. Right? From the second equation here, I can cancel 3y from both sides, and I get z equals 0. Or you can even say that from the third equation here, if I subtract 3z from both sides, I get z equals 0. Of course, another way to do this is you just compute reduced echelon form. You can also find the same thing. So if you have this here, then this says that this should be the span of simply one vector, namely 1, 0, 0. So of course, the reason why this is true, this says that y and z have to be 0, but x can be anything. Right? This over here has no conditions on x. So that's why I have the span as this here. Right? Well, that's one case. Let's take a look at the next eigenvalue. So for the next eigenvalue, so this is lambda 2. So here I want vectors x, y, z. And again, let's take a look at the a times v on the left-hand side. So 3x plus y equals something. 3y plus 4z equals something. And then 4z equals something. So this is the left-hand side, a times v. On the right-hand side, lambda 2 now is 4. So instead of 3x, 3y, 3z, I'm going to put in 4x, 4y, 4z. Right. Now let's try to simplify things a little bit. So here now, I can't quite subtract things off the way I did before. I have to just be a little bit careful. So I notice from, let's say here, this system, if I subtract 3x from both sides, then I get y equals x. All right, so I'll put this here. All right, so again, subtract 3x from both sides, I get y equals x. From this one here, if I subtract 3y from both sides, I get y equals 4z. Right, again, subtract 3y from both sides to get y equals 4z. The last one here is a truism. It's true for every value of z. And so you can see here that once I give you z, y is uniquely determined. And once y is uniquely determined, x is uniquely determined. So really, z here is the free variable, and both x and y are the leading variables, right? They are both determined in terms of z. So I can write this here as the span corresponding to this one vector, 4, 4, 1. So again, once I know what z is, y is 4 times that, and x, which is y, is 4 times that. Right. So let's observe a couple of things here. The dimensions of both spaces is 1. We can take a look here at the multiplicities. So the multiplicity for the first space we said was 2. For the first eigenvalue we said was 2. Multiplicity for the second eigenvalue we said here was 1. So in this second case, they're equal, but in the first case, it's strictly less than. Right? So what we want to do is try to stare at these different numbers here and how everything compares. Right? So here is the main result. So the book calls this theorems 5, 7, 8, and 9. Right, we'll just continue all the notation as before. So the first statement is that the dimension of this subspace, right, so this corresponds to the eigenvalue lambda j, is at most mj, but at least 1. Right, so it's at least 1 is at most mj. You can see in these two cases that the example here has dimension 1, so the point is that the dimension is at least 1. Right, let me write the second property here, which is a little bit strange. But it says the intersection, lambda I and lambda j, this intersects in the trivial subspace whenever I is different from j. So you can actually see that over here. For the first eigenvalue, this space here sits inside of the yz plane. Right? I only have something that's along the x direction, right? 1, 0, 0. Over here, this kind of goes in a different direction. So this is a line in this direction, 4, 4, 1. And you can see that there's no way that these spaces here would intersect. So here, the intersection would mean these two hold true, y equals x, y is 4z, and those two are true, y equals 0, z equals 0. The only way y equals 0, z equals 0, and y equals x, y equals 4z is if I'm at the origin, x, y, z all equal to 0. But that's exactly what the second statement says here. The only way that these two spaces intersect is that they intersect at the origin. Right, let's do two more properties here. So next, let's let maybe here Si be a linearly independent subset of E lambda I. So if you will, you might think of Si as like a basis for this subspace. So then it says the union, let's call this S. So this is S1, S2 through Sk. Right, so if we'll think of this as like if I have a basis for each and every one of these, I combine all of these together here into one big set, S. Then it says this is also a linearly independent set. This is a linearly independent subset of V. All right, we'll try to give some examples of this in a minute. So now the last part here, this answers our motivating question from before. T is diagonalizable if and only if each M sub j is the dimension of each E lambda sub j. Well, remember that these here, this dimension is less than or equal to this. So what this says is I have to have equality on the nose for each and every eigenvalue. And again, we'll try to do an example of this here. So, moreover, if T is diagonalizable, let's let beta j be a basis of, let's say here, 4 E lambda j. Then this union is a basis of eigenvectors. So again, we'll try to do an example of this in just a moment. Right? So let me recap. So number one, if I take a look at each and every one of these subspaces, these E sub lambda j's, its dimension is somewhere between 1 and the multiplicity mj. And number two, this last part over here, is diagonalizable if and only if that dimension is as large as possible. And the way you can diagonalize T is you find a basis for each subspace, then you take the union of all of those, and now you have a basis of eigenvectors. So again, let's try to do a couple of different examples here to see what does this really mean. Right. So let's go back to the two previous examples that we had. This left multiplication by A in terms of this matrix A, this identity matrix. And we just found out that K equals 1, and our eigenvalue is +1, and our multiplicity is 2. Right? So what's happening here with this subspace, E lambda 1? So E lambda 1, this is the set of vectors such that A times the vector is lambda 1 times the vector. But now let's just try to multiply some things out here. So this is the set of xy. And if I multiply out A times V, then I get this. And lambda times V, well, lambda here is 1, so this is just xy. Right, so again, what's over here on the left? This is A times V. What's over here on the right is lambda 1 times V. But you see here that this is the whole space. Right? This is a truism. X always equals x, y always equals y. So this here is the whole space. And so the dimension is equal to the multiplicity. So this means right off the bat, without doing any more work, A is diagonalizable. In fact, I can diagonalize A by choosing the standard basis here. Right? So that's what the fourth part of the theorem says. I choose the basis for this eigenspace, for this E lambda 1. The standard basis works. That's the basis here for F2. Really, I can pick any basis that I want. Pick any basis you want here for F2. And then you see that, according to this theorem, that's the basis of eigenvectors for our transformation. Okay, let's do a second example here. So what about this other 2 by 2 matrix that we wrote down? Right. So now let's consider this left multiplication by A, right, in terms of our matrix A. Here, this is 1, 1, 0, 1. So also we found here that there's only one distinct eigenvalue, namely +1, and the multiplicity here, same as before, multiplicity 2. So let's try to do something similar to before. Let's try to compute this eigenspace, E lambda 1. So the set of vectors where A times V is lambda 1 V. So let's write this as xy and F2. So now let's take A times V. So the left-hand side, I get this. On the right-hand side, I get lambda 1 times V. Right, so again, what's over here is A times V. And what's over here is lambda 1 times V. Now, if I stare at this, now something different happens. Here, if I cancel out an x, I get y equals 0. The second equation here is a truism. So I notice in this case that this is simply the span of this vector here. Right? Again, y has to be 0. Right, y has to be 0, x can be anything. But if I stare at this now, this means that it has dimension 1. That does not equal to the multiplicity. So I actually see that A is not diagonalizable. So again, to recap, really it comes down to statement 1 and then statement 4. So statement 1 over here says that the dimension is bounded below by something, bounded above by something. And the last part here of the proposition says it's diagonalizable if and only if the m's here all hit right on the nose. So just to kind of maybe do a third example, we can come back to this last example that we did here with this 3 by 3 matrix. So let's just quickly write out what we had here. So let's consider this LA going F3. In terms of this 3 by 3 matrix. So this was 3, 4, 0, 3, and 4. Sorry, it should be a 1. 0, 0, 4. So we realized that there were only 2 distinct eigenvalues. The first one had multiplicity 2, and the second one had multiplicity 1. Right? Now we worked out that the first eigenspace we said was the span of this vector here, 1, 0, 0. So that means that the dimension of this first eigenspace is 1. For the second eigenspace, we computed that it is the span of 4, 4, 1. And its dimension was also 1. Now, in the first case, this is equal to the dimension of the multiplicity, so we're fine. In the second case, I should say here in the first case, this is not equal to the dimension. So, because I have a problem here, I can actually conclude that A is not diagonalizable. All right, so again, even though it's okay here for this eigenspace, it is not okay here for this eigenspace. This dimension here isn't large enough. I need to have another eigenvector here to make things work, and I don't. Okay, well, thank you very much for your time and attention, and good luck on the second midterm.